welcome everyone to this panel discussion. This is a panel discussion on that we call, it's a series of talks which is called the changing role of chemical engineers. And this is something that's been coordinated by the Department of Chemical Engineering at IIT Bombay. So this event really started out as an alumni engagement event. And so we started running this event about a year and a half, 2 years ago. And the idea was to really look at ways by which alumni and the department can engage. This is something that we started when my entire class came to campus for the 25th year reunion, and also then the class of 95 came to campus for the 25th year reunion. And so the idea was we've all gone out and we've done different things, and we're all over the world working on various different areas. How do we sort of use that to connect back to the department and to really see how IITB can contribute towards some of these emerging themes? So it's a very different kind of a panel discussion. What we do is we have primarily chemical engineering alumni, but also this time, for example, we have Srini, who's from what used to be called metallurgical sciences, but now it's metallurgy and material sciences department on campus. And so the idea is to pick themes that would be generally interesting for a wider audience, and also to assemble chemical engineering alumni, or broadly other alumni who are from the industry, who are industry experts, who've been in the industry for a long time, who are in positions of leadership, to really comment on what the trends are in these areas. And of course, since this is an alumni event, the idea is also to then maybe examine what is the role that IIT Bombay can play in leading and shaping some of these initiatives. So we've had several such events. So somebody had asked if we could look at recordings for these events. So this is the website che.iitb.ac.in/panel-discussions. And so on the website, you have all the previous discussions we've had. We started off with one on the pharmaceutical, with people from the pharmaceutical industry. Then we had one on air quality, energy transitions, medical technologies. I'm sorry. So the last one was medical technologies and not the energy transition. And today's discussion is around the role of materials in the economy and how does it intersect with the environment. So it's clearly an area which is of great general interest, especially especially in India, but also throughout the world. And the theme really is that when you look at the paradigm of how materials are used, these materials are typically used in a one-way fashion. So this is sort of a use and throw paradigm. We create these materials, we use them, and then they typically go into waste stream or into a landfill. And this is true across industries. It's true in construction. It's true for a wide variety of materials that we generally use. And now, as we have 7 billion people on the planet, and as aspirations to have a comfortable lifestyle that all of us want to enjoy, how do we do this in an environmentally sustainable manner? How do we do this without compromising the quality of the environment, and without compromising the future of the planet? So this is really something that's a very important area that we've all been engaged with as engineers. And so I'm delighted to introduce the panel that we have, and to talk to us about some of these. So let me introduce myself. My name is Guruswamy. I'm a professor of chemical engineering at IIT Bombay, and I work broadly in the area of soft materials. So that's a subclass of materials. We are interested in polymers, composites, colloids, and surfactants and things of that kind. I'm also the associate editor for a journal called Soft Materials, and one of the things that we are really trying to do is to have promote research in the area of sustainability. But let me introduce the rest of the panel. I'll briefly introduce them and then request them to each say a little bit about themselves and their journey. Our first panelist is Dr. Vijay Metar. Vijay got his master's from the Chemical Engineering Department at IITB in '94, and he's currently with Kraton and DL Chemicals. So let me just introduce all of them, and then I'll have them speak a little bit about themselves. Our other panelist is Dr. Sameer Ralhan, who's from a year after, who graduated a year after I did. And he's currently the CFO for the Chemours Corporation. We then have my batchmate, Srini Rajagopalan. Srini's been with Exxon for several years, where he's one of the leading R&D managers in the area of materials. And last but not the least, somebody who's much senior to us, Rajeev Pandia, who's been involved with Indian industry for many, many years and was also the former president of the Indian Chemical Council. So with that very brief introduction, let me go to the panelists and request them to speak a little bit about their journey, where they're at, and maybe just a couple of words about what they broadly feel about this area, and then we'll come back and take specific questions. Right, Vijay, why don't you go first?
Yeah. Thanks, Guru, and hello, everyone. It's a pleasure to be on the panel. A little bit of my background, starting with IIT journey. It started about 30 years ago. I was Professor Bellari's first student, and Professor Kurchatkar, who some of you may know, was the IIT Deputy Director. He was my co-advisor. And thanks to him, I ended up at doing my PhD at Texas A&M. He was A&M alumni. And after graduating, I joined GE Plastics, a division of GE at the time. And GE was, at that time, the most admired and the largest company in the world. And believe it or not, my first manager role at GE was to lead a small team to come up with new material technology, focusing on sustainability. In fact, that small team won the GE's first Ecom-Imagination Award back in 2004. So looking back, GE was well ahead of its time, focusing on sustainability initiatives in the early 2000s. Anyway, don't ask me how GE is doing now. But after GE, I went to work for General Cable, a global wire and cable company. And in 2017, I joined Kraton as the CTO. Kraton is a specialty polymer as well as a renewable chemical company. We are the largest manufacturer of fine chemicals in the world. And earlier this year, we were acquired by DL Chemical, a Korean company. And now I serve as the CTO for the DL Chemical Group.
Thanks. Thank you, Vijay. Sameer, would you like to go next?
Yeah, sure, Guru. Sameer Ralhan. I'm currently the CFO of Chemours, but my gosh, the journey has been highly non-linear since I left IIT. I left in '95. I went to do my master's and PhD at Rice, but somewhere in the middle, I started working full-time as well for a company called Aspen Technology. So almost for 4 or 5 years, I got a chance to work across the petrochemical sector. I pretty much lived out of my car on the Gulf Coast. It was a phenomenal experience, but just like how people are seeing the energy and what it's doing to the industry and broadly to the economies, that's what's happening. People forget, like, in late 90s, natural gas in the US was $14 MMBTU, and every chemical in the world was going to be made in the Middle East. So as a young engineer, I started thinking, okay, well, what does it mean, how the investments will happen? And frankly, that got really interested me into the business side of chemicals, and led to an MBA and led to almost 10-ish years on Wall Street with Bank of America and Goldman Sachs, and then finally decided to come back to the industry as this Chemours was getting spun off and created out of DuPont with a lot of DuPont legacy and heritage, and the liabilities as well. So just creating a new company. So it's been a phenomenal journey just to help shape this thing up. So I look at the issues on the sustainability side a lot nowadays, as you can imagine, from the financial side, right? It was interesting to see a lot of these things from the chemical side, from an engineer's perspective, and I get a chance to see it a lot from the financial perspective. And what I can say is, it almost 15 years back, when I go back and look at, you had to pull people into those discussions, right? There was stuff happening, as Vijay said, in the R&D labs, but if you went into the mainstream, it was a side show. And I can tell you right now, based on all the discussion that I have within our company, and frankly, a lot of the company leaders across the sector whom I got a chance to interact with, it is front and center into the strategy discussions, investment discussions. So the question is like, hey, Sameer, why now, right? What's happening? Why is it so central to the way companies think? And frankly, it's now, and I'll give you a very finance answer, right? So I'll provide a very different perspective on these things from the rest of the panelists. It's hitting all the financial statements now, right? You look at the P&L of the companies, you look at the cash flow statements, you look at the balance sheet, it's huge, right? So there are four things that are happening in the industry right now, right? First is on the cost side. I think we all look at the commodity prices, the way they're going. Frankly, cost was important. It has become a resiliency issue. Right? You take a look at the supply chains and everything else, you throw geopolitics on top of it. Again, I'll share with you some numbers, and people much smarter than me come up with these numbers, but it's almost like $1 trillion annual material savings, if you think about it, just on the cost side. So you've got the business leaders and the finance guys like me at their attention right now. So that's a number one. Second is a growth side, right? This is creating a lot of new economic growth opportunities. And for all those who are young and starting your careers, just think about this thing, right? This is almost like a $4.5 trillion economic output opportunity by 2030, 2035 kind of a zone, and 25 trillion by 2050. So just take a step back and think about where you want to be, thinking about investments, be in your career, and be, your interest is huge, right? It's bigger than Metaverse, it's bigger than YouTube, and it's definitely bigger than TikTok, right? So this is a massive opportunity. So once again, you got the business interest. And the third one is capital, right? Now you look at all the ESG-based funding source, both from the debt side, equity side. So that becomes a capital advantage as well, which is big, which was not there around 5 years back or even 3 years back. So that's one. And the last one is regulation, like a lot of reporting requirements coming up on the companies now. And all those things as you see the Google and the Microsofts of the world, and GM and Tesla pushing some targets, all that stuff has to get pushed down all the way down to the material suppliers. So the regulations that is coming in with respect to disclosures, for those who are familiar with the US system from the SEC side, are big. Right. So when you look at all those four things from a cost saving perspective, from growth, from capital, from regulation, there's tremendous stuff coming our way. And it's frankly, it's turned around from a headwind. It is becoming an opportunity. I think the companies who are going to take that approach are going to be successful in the longer run. So I'm pretty excited about it. And that's why I'm here today. And again, I'll happy to address any questions later on.
Thanks, Sameer. Thanks. Srini, but tell us more about your personal journey as well, and your professional journey, and where you're at right now.
Sure. Yeah. Thanks, Guru. And I should say, first of all, thanks to the CHE department for extending this opportunity for all of us to get together again. Like Guru mentioned, I am not a chemi guy, but I am your colleague from across the corridor, as I like to say it. But yeah, I mean, materials sort of cut across every discipline, and it's great to sort of be able to come back and talk to all of you on this platform. So I completed my BTech along with Guru, and then I completed my PhD in material science from Ohio State. After completing my PhD, I joined GE and worked there for several years in Bangalore. So there I got the chance to interact on a wide variety of material systems. GE is, of course, as most of you know, at that time, definitely it was a very diverse materials-based company. So got the chance to work on a huge range of materials platforms. And since then, I've been working with Exxon. So I've been with Exxon for about 13 years now. So Exxon is, as you know, diversified oil and gas company, but also a broader energy company now. So our group in Exxon does a lot of work on multiple materials platforms. So we are based in Clinton, New Jersey, as part of Exxon's R&D organization. So as the name suggests, right, we work on metals, alloys, high temperature materials, composites, so a whole range of material systems to enable technologies and solutions for our current operations. But as we and the rest of the world, get deeper and deeper into the energy transition, the role of materials in enabling energy transition becomes more and more critical and important. So whether you look at areas like hydrogen or CCS or even plastics or polymers and the role of new and advanced chemicals and other technologies, I think materials start to take more and more of a central discussion item in all of these areas. So I think that this panel and this discussion is extremely timely for where we are today as a society. And thanks to Guru and IITB for pulling this together.
Thank you, Srini. Rajiv ji, can you please tell us about your personal journey? I know you've been sort of a doyen of the industry, and so we'd love to hear more about where you're at and your brief thoughts on this panel.
Sure, thank you. I graduated from IIT Bombay in '71, and I had two career choices at that point of time. One was to go to IIM Ahmedabad, where I had secured admission, and the other was to continue in chemical engineering. And I opted for the second of the two options and have remained in the chemical industry all through my career. I went to Stanford to do my master's in chemical engineering, returned to India, and my first job, as Sameer mentioned, it was a digression from hardcore chemical engineering to chemical project evaluation. I joined ICICI Limited, which at that time was not a retail bank, but a development finance institution, appraising chemical projects. So I had been associated with the technical and commercial evaluation, as also financial evaluation of several chemical projects which were being set up at that point of time. And the Indian chemical industry was just kicking off. So it was like being part of the growth process. It was also like doing an MBA and getting paid for it, because I learned finance, I learned marketing, market research, and it was extremely interesting. But then I felt that to be more effective, I had to go through some project cycles myself. So I went through several project cycles over the subsequent few years, setting up a carbon black plant with Phillips Petroleum Technology, some agrochemical projects with Shell Technology in NOSIL, and then projects dealing with elastomers such as EPDM, polymers such as polybutene, specialty chemicals such as phenol and acetone derivatives. So I was in the project management field for a few years, then moved to strategy, which included project identification, development, technology evaluation, identification, technology transfer, going all the way to various facets of project monitoring and completion. In '92, I moved to general management, but again of a chemical company, Herdelia Chemicals Limited, when I took over as its managing director, a position which I held for 16 years, during which there were several changes in the ownership of the company. And eventually it was acquired by Schenectady International of the US, which is now called SI Group. And it was a very interesting journey where one was moving from one set of multinationals to another with different philosophies, different ownership pattern, different culture, and I thoroughly enjoyed the transitions. After I retired, I joined the boards of several Indian and foreign companies, and also began advising them, especially in the areas of strategy, project management, operational excellence, and organizational development. Currently, I'm associated with a few chemical companies in various capacities. And out of these, two companies are very active in the subject that we are going to discuss today, namely recycling and treatment of solid waste. One is GRP Limited, a company which is one of the largest in the world in recycling tires. And very interestingly, it was started by an alumnus of IIT Bombay, Mr. Rajeev who was in our batch of '71, metallurgical engineering. And that company has grown and is today supplying reclaimed rubber obtained from recycling of tires to 7 of the largest 10 tire companies worldwide. The second company which is active in this area is Excel Industries Limited. Though its main business is agrochemical intermediates, it deals with municipal solid waste and now construction and demolition waste. And it is looking at various other opportunities along the whole waste value chain. So these two companies especially have given me significant exposure to this area of solid waste management, which I think has become one of primary importance for chemical engineers in terms of innovation, entrepreneurship, business development, and of course, environmental necessity. So this in a nutshell is my career path.
Thank you very much. Thank you. So is to sort of provide maybe a broad kind of a definition of what we're going to talk about. Now, the area of sustainability, of course, is vast, right? And when we talk about sustainability, sustainability involves not just materials, but also energy. And it's really this nexus between all these different areas that constitute sustainability. In fact, one of our previous panel discussions, we focused largely on the energy transition and looking at decarbonizing the economy and so on. So just in the interest of keeping things a little bit more focused, the idea here is to talk largely around materials and how materials interact with the environment. And like I said, our paradigm primarily has been that we create these materials, we use them, and then it goes into some kind of a landfill or some kind of a waste stream. And Rajeev ji, for example, spoke about recovering materials from the waste stream. So the question is, given that the resources that are available to us are finite, how does one as an engineer look at this problem? Are there there are principles of sustainability and green chemistry that have been expounded, right? The idea of recycling materials, of course, but before that, the idea of refusing to use materials, also looking at reducing our usage. So given that the issues are very complex, I thought what would be interesting is to sort of define that we'll speak largely about materials, but also think a little bit about the materials energy nexus in the context of understanding the life cycle of materials, right? So when we think about materials and sustainability, there is a cost that comes with, for example, recycling material, right? What is that cost? What does that involve? And those are important aspects that we need to think through. And of course, in all of this, we recognize that that this fundamentally means that the students who are entering the workforce today need to be trained to think of these concepts and understand how to apply some of these concepts. So that is again a big part of of the thinking that we want to sort of address during this. So one of the people who really pushed this idea of sustainability is the Ellen MacArthur Foundation, that has really come up with this idea of circularity of materials and circularity in the economy, which is that rather than take these materials, use them and throw them away or put them in a waste stream, how can one use this so that you don't degrade the value but keep using this? Now, of course, this comes at a cost. The cost is very often measurable in terms of energy. And so what is the trade-off here? And how does one understand what's now called the life cycle analysis for these kinds of materials? So with that broad background, what I'll do is I'll first address a few questions to each of the panelists and maybe have a little bit of discussion around that, and then we can address some of the questions that you sent to us over when you filled the registration forms. So let's start with Rajeev ji. Rajeev ji, you have a very broad perspective of the materials industry, having served on the boards of several different companies, and like you said, being closely associated with both GRP as well as with Excel, and of course the fact that you were the president at the Chemical Council. Now, one of the things that's clear is worldwide and also in India, we are transitioning to an era where there is a much more keen awareness of the finiteness of the resources that we have, right? And this cuts across industry. It's not just the chemical industry, but it's also construction, it's agriculture, it's polymers. There are some challenges that are general and that are broad and that cut across geographies, and then there are also challenges that are unique to India. So can you give us a very broad perspective on your thoughts around these?
Sure. Let me answer your question in three different parts. The first is, let's look at the dimension of the problem. Globally, every day, we use 1 million tons of plastics, polymers. And out of that, only 8 to 10% gets recycled. Now, this itself shows how large the problem is. But later on, I will show that plastics is a relatively smaller problem, and there are much bigger problems associated with a few other types of solid waste. When it comes to India, we are 1/6 of the world's population, but our consumption typically is much lower. And if you look at any commodity, typically we are at about 1/10 to 1/12 of the world's consumption. And to that extent, the problem is slightly less for us than for developed countries such as the US and Western Europe and so on, where solid waste is mounting at a much faster rate than it is mounting in India. However, this is a warning sign for all of us as to what has been happening in the West, and this is the time when we need to really look at our practices to improve. Let me give you some numbers to show the dimension of the problem first. Rubber and tires. Globally, the use is 30 million tons. And in India, we use about 2 million tons of tires, which means per person per year, that is per capita, it is 2 kilograms. Every year, 2 kilograms of tire gets accumulated. The problem with polymers is much larger. Globally, it's close to 300 million, and in India, we use 22 million tons of polymers every year, which is 16 kg per capita, growing at about 8 to 10% per year. So this is a problem which is going to continue to grow and double every 5 or 6 years. Then we come to paper. We use 18 million tons in India, which is about 13 kilos per capita. Glass, about 3.7 kilos per capita. But much bigger than these is the problem of construction waste. There are no reliable estimates, but one estimate is that we have about 150 million tons of construction demolition waste coming up every year. But if you look at the fact that we consume 328 million tons of cement, and to the cement is added aggregate and sand and bricks and so on, and I'm sure the number is closer to 250 million tons than 150, which translates into almost 269 242 kilograms per capita. And similarly, agro waste, 350 million tons of agricultural waste. So if you add all this up, just these 6 categories of solid waste, you come to 550 million tons, which is equivalent to 423 kilograms per capita. Now, these numbers might sound esoteric, but if you convert that into relatable numbers, assuming that an average Indian weighs 60 kilograms, 60, an average Indian generates 7 times his or her weight every year, year after year, as solid waste. Now, this is a huge problem and also a huge opportunity. And this is the dimension of the problem that I wanted to highlight. At the same time, in India, we have a few advantages which are very endemic to us. First, we have a long history of recycling. Even from my childhood days, I remember people coming to individual homes, picking up newspaper, picking up glass bottles, picking up plastics, metal. So we have this tradition and an ecosystem built around recycling, which Western countries did not have at that point of time. At that point of time, there was no consciousness about environment to the extent it prevails today. So we have a long history. The second is the labor intensity of recycling. From collection to segregation to processing to the whole value chain of circularity, or even combustion or whichever, it involves substantial labor. And this could be a threat or an opportunity depending where you are. In India, not only is labor cost low, but we need employment creation. So this, in fact, provides a great opportunity, not only to the scavengers in the street, but those who have some higher level of contribution to make in terms of segregation and then down the value chain. So I think this is a second advantage India has. The third is entrepreneurship. When we see an opportunity, we have people who are willing to grab it, and the finance is available. Their risk-taking ability is much greater in India than many other geographies. So we have a third advantage. And the fourth advantage is, as we move forward, we'll need more and more of IT intervention. And I'll give some examples later on if we have the time. And we would also need innovation. in terms of chemical engineering practices, mechanical recycling, and so on. This is still at its infancy, and we have a long way to go in circularity. And India is very good in both innovation and IT platforms. So I think these combination of factors can give us a great presence in this whole ecosystem of recycling. So this was the first part to your question, the dimension and the India opportunity. Now let me talk about the second part, which is the past and present practices of recycling or treating solid waste. When it comes to solid waste, there is a hierarchy or a pyramid. At the bottom of the hierarchy is landfill. And most of the waste currently goes into landfill. But we need to realize that 70% of the Earth's surface is oceans. That means only 30% of land is available. Now, on this land, we need to have housing, we need to have factories, we need to have roads, we need to have forests, we need to have farms, and there is no room left for solid waste landfill. In addition, landfill can lead to fires if it's organic waste. It can lead to insects breeding grounds and so on. So this is the least desirable of all the options for waste treatment, and we need to therefore necessarily move up from the bottom to the top. Next to landfill is combustion, and this is really uncontrolled combustion. Now every winter, especially in the north, we see how the stubble is burnt and the kind of environmental havoc that it causes. This is uncontrolled combustion. And it has fire hazards. I believe in one day alone in the north, there were 2,000 fires. And there is also tremendous pollution that we see in the form of smog. So this again is not an option. Moving a little further up is what you refer to energy. That is, you use cut tires in cement kilns, or you use polymer briquettes in boilers. So there is some harvesting of value, but it's just limited to energy and not material. This again is not an ideal situation. So we move next to a more organized way of treating waste, that is pyrolysis, which is again combustion, which is again energy, but you recover fuel out of it. And in the case of tires, one recovers carbon black. And therefore, to that extent, it is partial circularity. One gets some functionality out of the tire, not fully, but partially, with some liquid fuel and some solid fuel. If you move further up the hierarchy, there is the low-end material recovery, mainly mechanical recycling. And here, but before that, you get certain functionality, for instance, using rubber crumbs in asphalt modification for roads, or using plastic granules in asphalt modification, or making sports surfaces out of rubber granules. Now, this is one way of recycling, but at the low end of the spectrum. Then we move up the spectrum, we go to mechanical recycling, and that is, for instance, PET bottles into polyester staple fiber and into the t-shirts and so on, pillows. This is a higher level of recycling. And at the top of the hierarchy comes chemical recycling, which is complete circularity, where you break PET back, take it back to its monomers, ethylene glycol and PTA, or you take nylon back to caprolactam, or you take polystyrene back to styrene monomer, and so on. And there are companies doing that. Though for polyester, it's very uncommon, but there is a company called Polygenta somewhere near Nashik. They've developed the process by which one can take PET back to monoethylene glycol and PTA. And this therefore helps them make polyester filament yarn, which is more difficult to make than polyester staple fiber, which one can do with mechanical recycling. So this is the hierarchy of solid waste management. And that brings me to the third part of the question, which is what are the ways going forward? How do we deal with these issues as we go ahead? And I'll divide that into three parts, one for individuals, one for industry, and one for academic institutions such as IIT, Chemical Engineering Department. as far as individuals are concerned, there's of course the paradigm of reduce, reuse, and recycle. But what is equally important is segregation. Segregation at source. The efficiency of that first step will lead to the efficiency for the rest of the value chain. And this is where in India we are lagging behind the West, where you would see that there are receptacles for metal, receptacles for plastics, receptacles for paper, and for other waste. We still don't have that level of granularity. We are still struggling to separate solid from wet waste at a household level. So for individuals, I think this would be their responsibility going forward of segregation to bring value to the entire value chain. For industry, the question, the challenge or the target is to move up the pyramid right to the top so that we have full material circularity, and not only do we get energy back, but we do get functionality of materials back. And for institutions such as IIT, it is development of processes. Let me give 2 or 3 examples before I close. There is pyrolysis of rubber tires. And one can have a batch process where one can get only liquid fuels, but one can have a continuous process where one can get char. Now, if you move to the next level, the char can be converted to carbon black with a proper structure and proper surface area. And if you do that, that carbon black can go back to tires and really fulfill circularity. Or if you look at, say, breaking down polymers back to monomers, we will have challenges with various types of polymers. And there is significant contribution of unit processes and unit operations in this whole area. So I think there is plenty of innovation that could be done at the level of individual departments of chemical engineering and multidisciplinary departments in institutions like IIT. I think these are the challenges and opportunities for individuals, for industry, and for academic institutions. I hope that answers your question.
Great. I mean, that was a really panoramic view and wonderful. Thank you very much. And you know, of course, there's a variety of initiatives at different city levels in terms of the first part of collection and segregation. For example, in the city of Pune, I know that the municipality has contracted with the rag pickers so that they will separate out wet and dry. But also, in India, anything that is valuable in the waste. So very often, metal, glass, clean plastic will anyway get separated out and go into another stream. So which is at this stage of our development, something that can happen, but as we go up the chain, that's probably less likely to happen. But absolutely, and the challenges you talked about at every level, I think you've really laid out a map that we can follow during this discussion. Thank you. So one of the things that you mentioned is really as you go to these different levels all the way to chemical recycling is where this nexus of materials, energy, and the environment comes in, right? Because when you're talking about chemical recycling, we spend an enormous amount of energy making these very beautiful monomers, polymerizing them, and then you have to zip it back to a monomer. That's a very expensive kind of a proposition. And that's where I think a lot of discussion around things like detailed life cycle analysis and understanding the implications of each of these routes comes in. And so maybe I can address this to Srini. Srini, I think Rajeev ji has provided a very nice overview of the area. But can you comment perhaps on what you view as circularity, especially since you are at a large global corporation and you're outside of the country? What is your view in terms of understanding circularity of materials, and especially in things like what is the state of the art in terms of really understanding the impact of circularity, things like life cycle analysis and so on. Maybe you can comment on that.
Sure. Yeah, and so I should start by saying, Rajeev ji did a fantastic job of laying out the metrics, right? So maybe my thought was, maybe I'll try and come in more from the principles side, right? And maybe try to complement what he has already laid on the table, right? So some of the things are quite basic, and I think Guru, you touched upon it earlier, but I think it still bears some repeating to sort of build our way to how do we really assess, or rather wrap our arms around this problem and then try to come up with solutions, right? So let's all recognize a few certain basic principles, right? One, right? Today's materials value chain is largely linear, right? And what do we mean by that, right? We go from resources extraction to production and manufacturing and processing to utilization to disposal, right? And Rajiv ji said it, right? I mean, less than 10% of the materials go from the disposal state back into some form of recycling in today's economy, right? So I always like to think of this linear value chain and in terms of, okay, what impact it has on us, right? And our ecosystem, right? And I'd like to lay out the impact in the form of 3 E's, right? There's energy, there's emissions, and then there's environment, right? And if we need to understand that materials, right? I mean, us as a society taking advantage of the materials around us has an impact on the ecosystem in the form of these 3 E's, right? And then if we start imagining approaches to create circularity in the materials ecosystem, then we have to also imagine the impact on these 3 E's, right? So that's the key, right? So circularity, as it enables materials to be reincorporated back into their value cycle, right, through various means, right? They can be mechanical approaches, chemical approaches, biological approaches, whatever it is, right? Whatever approach you take, to imagine avenues to circularity, you really need to have to think about, okay, what does it mean to these 3 E's? And then what it means then is we have to recognize that, it takes energy to take this linear value chain and bend it all the way back to enable circularity, right? So there's some energy penalty, we can call it emissions penalty, and potentially some environmental penalty to be able to bend this linear value chain and to start to enable circularity. And therein comes in the topic of life cycle assessment and doing a true assessment of what it takes to enable circularity, right? And I'll talk about life cycle briefly, but I'll just introduce this 4th E, right? I mean, for us to take this linear chain and bend it back, right, it also takes money. And that brings in the 4th E, which is economics, right? And life cycle is the first step, right? Through life cycle, what we do is we have to first come up with a clear and a concrete understanding of what it takes to be for us to enable the circularity, right? So what that means is drawing the system boundaries the right way to be able to understand what is the true value that a material or a set of materials imparts to us, right? In the context of what it is intended for. And then what is its current end of life situation right now? And then you start to think about, okay, if you are enabling circularity, what does it take in terms of energy or emissions or other items to be able to enable that circularity? And then be able to say, okay, if you have an X in terms of whatever parameter it is, there is a delta X involved in getting back into the circularity, right? And many times it's important that we do not use this life cycle philosophy in a narrow context, right? I mean, if we use a very narrow context to do that, we might end up with some answers that are suboptimal or may lead us down some rabbit holes that may not be the right ones, right? So the bigger and the broader we draw these system boundaries to enable true and complete life cycle analysis, the better off our understanding and eventual answers will be in this. And that also is important because it helps us inform that 4th E, right? I mean, sometimes we might come up with answers and solutions, but they might not be the most optimal techno-economic answers and solutions, right? I mean, life cycle is the first step, but you have to feed life cycle into what I call as techno-economic approaches to understand circularity, right? So going from LCA to TEA, right? I think that is the key because the society is all about creating solutions in the most economic manner possible, right? So to be able to start with LCA and then go to TEA and then being able to complete the loop in the most comprehensive manner possible is where I think our approach is like. And when you start to look at all of this, then we have to say, then we can take a step back and say, okay, do we have an accurate understanding of materials value stream? Do we have an accurate understanding of the life cycle? And now, does it give us an opportunity to consider novel technologies that allow us to enable circularity at the lowest possible cost with the maximum possible impact and value? And I think that's the way I try to look at circularity and the impact of LCA and techno-economics.
Thanks, Srini. That's very, very it's nicely laid out. But so one of the points that Rajeevji made is in terms of the per capita usage of rubber and plastics and other materials. Things like construction waste and in terms of just mass per person per year, there's a lot more of that. But if you look at the impact that things like plastics have on perception, and also in terms of government legislation. This is something which is a very visible kind of a situation. Also, for example, we recently had some legislation focused on single-use plastics and so on. Any quick comments on that, Srini? Then can move.
Sure, and I'll try to maybe offer a few thoughts, but within the same principles that I just tried to lay out, right? I mean, when you think about plastics, right? I mean, let us all recognize that plastics exist because they serve a certain set of societal needs, right? And some examples of the societal needs are things like food preservation, clean water, enabling clean energy, good health, right? I mean, plastics play a critical role in all of those things, right? So why not not to dwell too much, right? We all, as a society and as a group, we understand very clearly that it's a need for us to minimize plastic waste, right? I mean, none of us is sort of shying away from that topic at all, right? So when we first lay out that question and say how do we minimize plastic waste, then we also have to ask the corollary question, which is the presumed selection of next best alternatives, right? Whether it's metal or glass or paper or whatever it is, right? We need to understand that selection within the context of what it means to the overall life cycle, right? I mean, there are approaches that you can take by drawing the box in an arrow fashion to say, hey, you know what, you just need to ban use of plastics, right? Because of so and so reasons. But then you sort of draw the box a little bit bigger and a little bit broader, and then you say, okay, maybe plastics as a family of materials, right, has certain life cycle advantages compared to your next best alternatives, right? And then that leads you to the question. It's not a question of just arbitrary positions or arbitrary action that may lead to suboptimal outcomes, but rather the broader question of how do you enable a true material circularity, going back to the same principles of energy, emissions, and the environment, right? So again, coming back to the same principle, we all recognize and share the belief we need to minimize plastic waste. So what can we do, right? I mean, I think Rajeev laid it out. When you talk about plastic waste, there are two main approaches. There's mechanical recycling, right, where you could take plastic and reintroduce it back into somewhat a downstream point of the overall materials economy. Mechanical recycling is good because it takes less energy, but also there is the potential debit that the properties continue to degrade over a period of time, right? So it's not complete circularity into perpetuity. And that is why I think you need to consider sort of other avenues like chemical recycling that take you back to maybe the front end of the value cycle, because you're breaking a material down to its molecular level building blocks, right? And then chemical recycling would be the avenue by which you sort of regenerate properties as well as materials, and then you sort of build the whole value stream and the life and the application cycle all over again, right? And Rajeev said it earlier too. For all of this, the critical first point is adequate waste management infrastructure. If we do not have that first critical point, then the rest of the points become that much more difficult to execute. So let's start there with adequate waste management, and then be able to use either mechanical or chemical recycling as the situation dictates to be enable the right type of circularity and solution.
Thanks. Thank you, Srini. So sort of continuing that train of thought, so of course, in the hierarchy, there is landfill, and then there's plastic to things like oil, but these are really suboptimal, right? So we're at least looking at perhaps thermomechanical recycling, and that's something which India has done really well, in the sense that if you go to any village fair, you'll see these multicolored buckets, which are really small scale processors who buy waste plastic and put that together. But that is very suboptimal, right? In terms of the properties, virgin plastic properties are far superior. So if you're looking at, for example, a large MNC that's looking at packaging, they're never going to be able to say that this is good enough, right? This is just simply not good enough. So Vijay, maybe you can tell us about your thoughts broadly in the area of, let's look at thermomechanical recycling. What are the prospects in this area? What are your thoughts around that?
Yes, absolutely. Happy to share that. The mechanical recycling has been around for a long time, right? For decades, but really it hasn't still become a mainstream solution. What I feel is the two challenges. It's cost and performance. And I'll share my own experience with this, because Kraton we believed that we had a technology that could solve this mechanical recycling problems. And when I was trying to put this business case together, and this is going back 2018, in that same month, I was trying to make a case and put it in front of our management. The largest recycling company in California filed for bankruptcy. And the same month, one of the largest petrochemical companies was in the process of commissioning a 1 million ton polyethylene plant. So it really, again, reinforces this cost and performance are issues. So recycling, especially the post-consumer recycling, is expensive because you got to, as earlier Rajesh said, Srini highlighted, collection. Then you got to sort it out. Then you got to transport. Then you got to reprocess it. All of this adds cost. And then on top of that, there is a performance issue, especially when you have recycled plastics that is mixed. Even if that is not the case, recycled plastic often has poor properties compared to virgin. But if you have mixed recycled, then the properties drop significantly. Even chemically similar polymers, you can't recycle easily. Guru, you mentioned about, you can make buckets. Yes, absolutely. So low-end application for flower pots, yes, you can make. But anything that is engineering, it is very difficult to come up with particularly based on the mixed recycle. So what's the way out there? Right? There are many technical approaches people have been looking at. Kraton has been looking at that as well. One of the common approaches is that you add a small amount of compatibilizer that helps improve the properties of either clean recycle or of a mixed recycle. And our own experience is that, Kraton has been making these compatibilizers since 1960s, and we knew that these work very well. But there was really limited market for it. 3 years ago, we redesigned and relaunched the products under Circular Plus, and that goes back to Sameer's comment earlier in his opening comments, that we are now seeing very nice traction, a lot of customer pull related to these product lines. And that's because many customers, ours, including consumers, they're asking for it. So overall, what I feel is that the mechanical recycling of clean, uncontaminated plastic works, and it has already been demonstrated in many places like Japan. I mean, very efficient in mechanical recycling. But when it comes to mechanical recycling of mixed plastic, we have a long way to go. For that to become mainstream and high value, there are multiple areas we need to focus on, from consumer awareness, and I think Rajeev talked about that earlier on, to designing the product so that you have a minimal number of plastics, material selection. You need infrastructure investments. We're going to be able to sort, transport, process these. We need infrastructure. As well as, along with that, there's some help from the government, right? In many cases, when the performance is low and the cost is high, the government can step in and help. And lastly, of course, the novel technologies. I know that there are many companies who have been looking at unique and interesting technologies to be able to handle mixed plastics. Interestingly, many surprisingly startup companies have been looking at that. So I think a lot of progress is being made along these areas, but I think it is a complex challenge for all the number of reasons I highlighted earlier.
Thanks, Vijay. Just a quick sort of a detour in a sense is, we've largely been speaking about petrochemically derived polymers. Your company has also been looking at naturally derived polymers. Are there what do you see as the opportunities there? Because one of the big challenges, right now, things like polyethylene and polypropylene, their properties are very difficult to match, right? If you're looking at packaging applications, some of those, it's very hard to beat those. But I think there's going to be a growing awareness of the need for perhaps substituting some of that with naturally derived materials. Do you have any comments on that?
Sure, Guru. I mean, this is certainly an exciting area. The bio-based plastic, bioplastic is an exciting area, but it's also not without debates and rather confusing, I would say. when generally when we ask people, what do you think of bioplastics, they say that it must be made with chemicals, monomers derived from biosources and biodegradable. But not so. When we look at the bio-based plastics, many of the current products today are made with monomers made from bioresources, but those are equivalent of petrochemical based. For example, there are companies who make now polyethylene made from ethylene derived from biosources like sugarcane or corn.
Yeah.
But ultimately, you end up getting polyethylene that is identical to polyethylene from petrochemical route. We have launched similar products because our customers are asking for it. We just recently launched a product made with biopyridine. So clearly there is a customer there, there is demand there. But they address one aspect of sustainability is that instead of making the product from fossil resources, now you're making it from bioresources. But are they truly sustainable? I mean, that's quite debatable, right? First, these plastics possibly divert the food resources, right? From what we now know is already stretched global food situation. Like taking corn, sugar, other resources to convert that into plastic. But the second thing is that they have the same challenges of biodegradability. And then there is this class of biodegradable plastics. I'm sure that we all seen this development of polylactic acid, particularly in the area of single-use plastics. It has been around for quite a while. It has gotten traction. And excitingly, I would say, what I would say, Guru, is that there are a lot more bio-based, biodegradable polymers on the horizon. The one class is called ChEA. Some interesting developments in the area. But of course, all of these at the moment currently lack in scale. They're quite minuscule compared to the traditional plastic. But I believe that with scale and with the proper support on all the areas, they can become mainstream, especially if for use in a single-use plastic areas. So bottom line is that I think the recycling of the plastics is a complex multi-dimensional problem, but the complex problem also means lots of opportunities for innovation.
Thank you. Thanks. Absolutely. And I may add probably that it is engineering innovation that we're looking at. And so, again, something that Rajeev ji pointed out in terms of opportunities, I think, especially for the students who are joining us, there's tremendous opportunities in terms of what chemical engineers and materials engineers can deliver in problems like this. So that's, I think, a really exciting area to be in. It's a frontier area, and I think this is a huge opportunity for chemical engineers of this and the next generation. So let me come to Sameer. So Sameer, let's look at this very differently. Your focus for many years now has been, how do you finance some of this stuff, right? So what's your view on the financial aspects or the economic aspects of the situation? And since you're from Chemours, you work in specialty plastics, especially materials that contain halogens, and those are especially hard. Even when you talk about mixed plastics that contain halogen are especially challenging, right? So what's your view on that, both in terms of the finances and also in terms of halogen containing plastics?
No, thanks, Guru. I think the first part, as you kind of talk about the financing, right? It almost connects to the point that you just made earlier, and what Vijay was saying. It's ultimately helping. One of the big things for us as an industry, I think this is where chemical industry has just do a better job, and all of us, is helping people understand the value proposition, right? I mean, Srini said, these. Fine, you can draw around the chemicals and say, hey, it's bad for the environment. This is, can't recycle, can't do this thing. But the alternative is worse, right? In some case, a lot of the bio stuff is in a kind of a similar kind of a domain. Yeah, you can get the sugarcane, all that kind of stuff. Who's going to look at the agricultural runoff, right? Which is mucking up all the water systems and everything else. The problems have to be looked at more holistically. But having said that, I think on the financing side, it's been pretty interesting for me to watch on the chemical recycling side, right? Because I think we talked quite a bit about the mechanical, thermomechanical side. The holy grail is on the chemical side. Can you get to molecular recycling stage and level, right? Can you even get the polymer out in a way that its integrity is intact, so it can be recycled, and frankly, you save a lot of cost if you can do that. To me, what I find is pretty interesting how the economics have started becoming pretty attractive. I think I'll share some of the examples, and these are non-Comores, and then I'll get to a Comore specific one with respect to halogens, and we'll address that. Look at the $1 billion kind of molecular recycling plants being set up the likes of Eastman, right? Almost like 3 plants now, where you essentially, as Rajeevji was saying earlier, or Srini said, you can take the PET effectively. Now it has to be neat, clean, much. This is where the upfront segregation comes into play. You can do that, and even the colored PET, right, with all the additives and stuff, you can get it down to the molecular level. Now that's holy grail, right? I think that's where the society is willing to pay a little bit more, right? That's the thing. There's a better understanding, and underlying all that stuff is the commodity prices are going up, right? If you fundamentally believe either through some artificial mechanism, what Srini said, put carbon tax and all those kind of things, and can bend the curve from linear to become it circular, or even there people can do a lot of lobbying and all that kind of stuff. But if the fundamental commodity complex is going up, and if you say, hey, these investments are not like 1 year, 2 year investments, right? It is a 5 year, 10 year, 15 year. If the curve has moved, it's going to be structurally higher. And I think a lot of these things start becoming pretty interesting. You're seeing, Lyondell now getting into molecular on the polypropylene side. It's been pretty interesting to watch that. But they are getting down to the monomer level. So from a financing perspective, what I would say, Guru, is the project financing as well as the companies themselves doing it. I think you're seeing that more and more receptivity because there's an end market out there, and people are willing to on the customer side. People, as we just said, right? Customers are willing to sign long-term contracts to that, right? So it's again one of those things. Hey, can I get my capital back, and can I return the capital back to the shareholders, right? So I think that part is looking more and more attractive, which is good to see. But again, a lot of that stuff is really, as you said, Guru, when you get into thermoplastic, is still more on the polyethylene, polypropylene, PET, of course, the biggest one, right? Because the velocity of that polymer is high, right? Single use, so velocity of the polymer is very high in the economy. So you use that, but halogens is a little different animal, right? Any polymer that contains halogen, right? And I'll just use 2 examples just to help illustrate that. One is on the PVC side, and then we practice more on the fluorine chemistry. So we are one of the largest fluoropolymers company. And on the anytime you add in the chlorine side, actually the carbon equation becomes lesser, right? A little less than half of the mass of a PVC is essentially chlorine, right? It's not actually carbon derived. But anytime you touch a halogen has come out, there's a lot of environmental sensitivity around these things, right? You think about PVC and the construction waste. Rajeevji said about the construction. Think about, maybe it's less in the Indian context. I don't have that much awareness, but thinking from the Western context, and especially the US context, right? As a housing, there's a lot of PVC use. Look at the infrastructure, water pipes, sewage pipes, all it's all PVC now, right? So think about all that waste being generated. And there's a lot of sensitivity around on the chlorine side, and there's a very unique structures, and the life of material is very different, right? When you start looking at the even the rubber side, right? It's a decently quick life cycle. You put a PVC stuff, unless there's a construction waste and all that kind of stuff where you're destroying a home after every 5-6 years building. Anything that's going in, PVC can stay out there for a long time, right? So that's why you use in the infrastructure pipes and all that kind of stuff. Now, a lot of the stuff, actually, I was talking to some of the guys, is it coming out, and it has additives, which in today's day and age, they were done like 30 years back. Those additives would not be, nobody wants to even like mechanically process that. So I think that's where the chemical recycling ultimately will have to come in. But the problem with the PVC side, and the biggest challenge, and that's really the challenge for the engineers and for the industry and R&D, is how can we get either get to the monomers or get the polymer out. Chlorine moves, right? And the basic things like hydrolysis and all are difficult to make it work, or at least until now, we haven't been able to make it work. Fluoropolymer is actually a very interesting situation, right? You kind of look in at least known to mankind, fluorine and carbon bond is one of the strongest bonds out there, right?
Yeah.
Which ultimately was the reason why it got used in a lot of the applications, right? And that became a problem as well, right? Because then they don't disintegrate, right? They don't degrade, right? And actually now when you start looking at the recyclability issue, we've been investing a lot in R&D on that front, Guru, is actually we can turn that thing which has been a disadvantage now in the last decade and a half or 2 decades for the fluoropolymers, actually we can turn the problem on its head and actually make it an advantage. And by that, what I mean is essentially we are working and it's pretty exciting results is actually if you look at, fluoropolymers in a lot of the applications that they use, for example, films in the electrolyzers and in the fuel cells and anywhere there's a film is used, you can actually hydrolyze that polymer pretty relatively easy, right? And that essentially means you can recover the polymer itself. You don't have to go to the monomer back, right? You can extract all the impurities, you can extract everything else that you added to the system, use it, and you can cast a membrane again, which is has been pretty phenomenal R&D for us. Which if that's kind of works, that can be very interesting. And there was a question I think that popped up on the pyrolysis and all that kind of stuff. Anything that contains halogens, pyrolysis doesn't work, right? I mean, then you're going to throw HCl and all the stuff up in the air. There's way more damage to this thing, right? So that's why the traditional stuff does not work. So I think the interesting stuff from R&D perspective, Guru, right now with polymers containing halogens, especially for us on the fluorine side, is how do we take the advantage of the strength of the carbon and fluorine bond, which again, as I said, it was a big advantage because they grow. Everybody hated them because now they can't, because they don't degrade in the environment. And now actually you can turn it around, you can actually and make it work. And there's one other big advantage when you get into the fluoropolymers kind of a world which is actually the cost to make is very high, right? So you're going from polyethylene, polypropylene, PT, cents per pound products to something which is multiple dollars, if not tens of dollars per pound or kilo kind of stuff, right? So actually the cost equation that has been raised, point has been made, there's a lot more room on the cost side if you can recycle, right? So that's where the chemical recycling is actually presenting some pretty interesting opportunities on the fluoropolymer side. Now that's the biggest challenge. So PVC is really kind of, kind of stands as like an ugly duckling, so to speak, in the middle. On the other hand, your cents per pound guys. On the other hand, your fluoropolymer guys, where actually if you can make the chemistry work, and we are seeing some really promising signs in our R&D on that works. PVC is kind of in the middle. It's very, everywhere. Yeah, chlorine, if you release in the environment, HCl, all that kind of stuff has a lot of damage. Like typical thermomechanical stuff, you do pyrolysis, HCl coming in, it's going to corrode your pipes and all that kind of stuff. You have to have a separate system. Like PVC getting into the current recycling systems is bad, right? It'll, even in the molecular recycling, it'll deactivate your catalyst. So halogens, what we are finding, at least on the fluoropolymer side, is it has to be a chemical solution. And that's where we're seeing some early signs and early successes. And this is where a lot of the R&D dollars, frankly, we are spending. Okay,
great. Thank you. So we're sort of almost at a little over an hour. So let's take a few of the questions that came in via the registration form, and also some that have been posted here right now. So several of the questions are around legislation and government intervention, or maybe even consumer education. So Kirkrani and Olina have asked about issues relating to legislation. There's also other questions that came through the registration forms that talk about, for example, how do you look at, when someone claims that there is there is a certain recycled content, how do you establish ways of verifying that? Rajeevji, maybe you can take that and tell us more about what do you think is a regulatory framework, and what do you feel is the role of possibly government intervention in terms of regulations and so on?
Yes, so let me take the last question first. How do you establish that a certain percentage of recycled material is indeed present in a product? For that, the government has worked on an audit process. So there are certified auditors who would need to give out certificates, and this will become very important because the EPR, the Enhanced Producer Responsibility, has already come into force, both for polymers and for rubbers. And therefore, for companies to avail of this legislation, they need to get certification from the authorized auditor, and they will follow a certain process. So so long as people are honest and keep their books properly and so on, which is of course a challenge in India, because already one hears about certain unhealthy practices in this particular field. But I'm sure there'll be ways found to get around them. There would be proper audits done. Now, in the West, for instance, there is this whole material balance concept. That is to say, the waste plastics or waste rubber go through pyrolysis. You get the oil from the pyrolysis process, which then become the feedstock to the cracker, steam cracker, and you get certain polyethylene, polypropylene at the end of the pipe. And then you relate what has gone in and what has come out, and the material balance principles, and you establish that your product is 10% green or 20% green and so on. Now, this, of course, does not look at the energy part, and if the energy part were to be added, it would be a totally different equation. But I'll leave that aside. To come back to the legislation, there are two important legislations that the government in India has come out with. One is a ban on single-use plastics. And this has been talked about for quite some time, but it has now been enforced. So very thin plastic bags, carry bags for groceries and so on are banned. Water bottles, cutlery, plastic cutlery. So anything that can be used only once and thrown away would be out of the system. The focus is going to be on plastics with long life. For instance, what Sameer mentioned, PVC pipes, which can stay in place for 50 years or 60 years, is a much lesser of a problem in the current context than very thin plastic films which clog outlets and therefore cause flooding during monsoon and drainage issues. So single-use plastics have been banned. This is one. The second major legislation is EPR. Now, EPR is being treated separately for rubbers and separately for plastics. For rubber, companies which use rubber, such as tire companies or conveyor belting and transmission belting and so on, they will need to buy certificates. And these certificates will come from recyclers who either convert rubber back into reclaimed rubber or through pyrolysis or through crumb rubber. So there are various weightages given to each of these end applications. And they will need to buy certificates. So this is some kind of a polluter pay principle, where if you are creating value out of material which is of a finite nature, you need to pay cost for it. And eventually the idea is that in buying certificates, there will be a price discovery mechanism which would come in play. There will be a certain price attributed, which will be indirectly the cost of the whole recycling process. Because in many cases, recycling per se is not very profitable. Mechanical recycling might be, but when it comes to chemical recycling, and as Sameer mentioned, the low-end polymers, where the headroom is much less, the margins are quite slim. And in India, where typically one sees a certain vacuum, many more people rush in, and the result is depression of prices and margins. So in many countries, it has been found that one needs government support, some fiscal support. In Europe, it is in the form of tipping fees, where at some stage in the value chain, some amount is being paid, which goes into the recycling equation. In India, it will be for rubbers buying of certificates. And in the case of plastics, it's not even buying, it's mandated. So for instance, in 3 years from now, if you buy some food product in a plastic bottle, or if you buy paint, or if you buy lubricant oil, 70% of that will have to be recycled material. And there are no options. One can't even buy something. Now, that having been put in place, that consumers of packaging products are now trying to find innovative ways to come back with the product which is the properties of a product made from virgin material, but at the same time has as high as 70% recycled content. So this is what government registration can do, when the government insists on something to be done. The technologies, for instance, Srini will agree that companies like ExxonMobil have come out with additives which would bring back some properties and functionalities to recycled materials. And there is more and more innovation. SI Group has recently come out with a series of additives. So this is the impact that legislation will have. But I think in addition to legislation and fiscal changes, and yes, there are countries which have brought in depreciation, enhanced depreciation for those who go in for recycling. There are concessional financing packages available for those. There are even green private equity funds, which provide private equity for projects which are innovative and in the recycling space. So I think this is one end. The other aspect is whether a consumer is willing to pay a premium for a green product. And we talked about biopolymers. So let me give an example. We have typical nylon 6 from caprolactam and nylon 66 made from arabic acid and so on. These have a certain level of price. But if you go for bio-nylon, that is, you start with the castor oil. And this is very interesting for India because India grows 70% of the world's castor oil. And from castor oil, you take the whole value chain to salicylic acid and then to nylon 12. Nylon 12 is biodegradable and you have a renewable raw material, renewable feedstock. But that nylon 12 is probably 4x the price of nylon 6 or nylon 66. But in Germany, people are willing to pay that price, and therefore the bags that are used for the waste which is collected, those are biodegradable. They are made from nylon 12. This is just an example. So a typical, or let me give you another example. In India, there is one company, India Glycols, in Kashipur in the north, which makes MEG from sugarcane. They have their own the crushing mill, they have their own distillery, they go to ethanol to ethylene, ethylene to MEG. Now, Coca-Cola buys this MEG, takes it all the way to Latin America. Now, here is Kashipur, which is landlocked. So you need to bring that all the way to Kadla, the port. From there, you ship it out to the other end of the world, to Latin America, because they can call the PET as partly green. PTA is still synthetic, but one of the two monomers is green because it is derived from sugarcane. So here again, it's a question of economics. There is a company which is willing to pay premium. So I think the economics challenges are partly solvable by government legislation, partly by perception of the people who are willing to pay higher price for green material, and partly through innovation, through better and better processes so the costs are brought down.
Thank you. So, Srini, maybe what we can do is, there's questions around perception and, for example, that driving, people who are willing to pay more for recycled products. Now, so one of the questions that was asked in the chat was, if you look at virgin plastic versus recycled plastics, given that there's going to be an increasing need for companies who are trying to source plastics to look at also circular plastics or recycled plastics, how do you sort of look at that problem? Right? How do you look at that and say, what's the opportunity there, and how do we get into those?
Yeah, so I think it's a broad question. Let me try to hit upon it maybe in two ways, right? I mean, this whole question of virgin versus recycled material, right? I mean, you have to think about it at a societal level. There's a need to generate awareness and advocacy, right? First of all. So what does that mean, right? That means, I always try to look at it as three apexes of a triangle, right? I mean, there's technology, there's policy, there's infrastructure, right? We need to sort of hit upon each of those apexes to be able to really move the dialogue forward in a meaningful fashion over here, right? I mean, Rajiv ji and others touched upon the topic of legislation and policy and things like that. Policy by itself should not lead the way too much, right? Because then you might lead to suboptimal outcomes, right? So we need to have technology, policy, and infrastructure work in concert around this, right? So what does it mean for this topic of virgin versus recycled plastic? I mean, the driver in this whole discussion is that we need to reduce the amount of plastic waste. right? So if we want to reduce the amount of plastic waste, let's generate the right infrastructure to be able to move the plastic waste so it can be recycled back. And then you have to be able to ask the question, if you are now in the process of recycling, can you get into sort of economically advantaged processes, whether it's in mechanical or chemical recycling, that allow you to get the polymer back into the value stream, right, at the right cost and the right price point, right? I mean, many people touched upon it, right? When you get plastics and polymers at the cost of cents a pound, and now you are asking society to pay a premium, whatever that premium might be for a recycled product, the society have the ability to sort of absorb that premium, right? And then continue to progress along its growth objectives. We all recognize sustainability, but we also recognize economic progress. So I think those are two ends, and we have to balance the tension there. So that's where technology comes in, right? I mean, if we can generate advantage technologies that allow us to recycle these virgin plastic streams, right? I mean, you talked about chemical recycling. I think there is enormous opportunity, right, for chemicals and materials engineers to be able to come together and say, okay, how do we generate technology, whether it's in the area of pyrolysis or co-processing or maybe other approaches, right, that allow us to take polymers back to their building blocks and then start regenerating the material cycle all over again. And if we can generate these types of technologies, we have addressed that equation, right? Then the society doesn't have to pay a premium for a recycled plastic versus a virgin plastic. I think that's the way I would try to maybe address that question.
Okay, great. So we've allowed the participants to unmute. So I think Rajaram Krishnaswamy has a question. So can you please go ahead?
May I?
Yeah, please.
Good evening. Wonderful to be in the midst of all chemical engineering alumni. In fact, Rajiv and I are classmates from the class of 1971. And so it's a pleasure to be with him. Now, I'd just like to inform you that, I attended a webinar a few months ago, wherein Professor Ashok Mishra, who was former director of IIT Bombay and famed chemical engineer himself and a polymer expert, was there. And he also had a colleague who spoke. His name is Sapre. He actually works for Reliance Industries. And Reliance has been doing a lot of work on the recycling of plastics. In fact, using it also for paving of roads. Now, I'd like to take the discussion a little away from plastics because that seems to be one of the points, but the main theme was on the circular mobility of materials. So I'd like to talk about a very important and a very relevant topic now, and that is about the recyclability of electric vehicle batteries. The International Energy Agency estimates the global demand for EV batteries as something like 340 GWH currently to over 3,500 GWH. And the focus on material supply chains and circular mobility is getting to be very, very important here. And in fact, China, which has the maximum amount of lithium and in anode and cathode production, has more than half the world's refining capacity. And that's where I feel that the resource efficiency is going to be very crucial in the interim. And fortunately, lithium batteries are almost entirely recyclable. And under idealized conditions, the retired batteries could supply over half the global demand for cobalt and lithium and manganese and nickel within the next 2 decades. But India has a major problem because India has a very low lithium battery manufacturing capacity, and we'll be almost certainly importing a whole lot. And it's not in sync with the government's requirement that we move over to electric vehicles. And so pushing battery manufacturing is one part, but recyclability of batteries is going to be a far major thing. Though we have a huge amount of reserves in nickel and manganese and copper and aluminum, and is the world's second largest producer of graphite, we have very, very poor resources in cobalt and lithium, and we have to import them. So I'd like to ask you fine gentlemen and experts on what you feel about lithium and the world moving towards EV. Of course, there are many companies in Mexico and the US, I know, and I've read about them. focusing on recyclability on lithium-ion batteries. In fact, Reliance Industries has also gone to sodium-ion and is going to, but it's heavier, and they're getting the technology from Britain. But could you please highlight something of what you might know and educate us on lithium and recyclability of lithium, please? Moving away from plastics for a while, please. Thank you.
So, Guru, did you want any one of us to take this in particular? Hello?
Yes, please.
I think Guru has dropped off. Maybe one of you could take this.
Yes, sir. I think a technical glitch happened. I will just call the sir and let them know.
Do you want us to wait a minute?
Well,
No, sir. You can go ahead.
Educates us and takes this forward. Srini, for example, or Sameer or Vijay.
I mean, I can offer a couple of views, right? I'm not an expert in this space, but I think you might have said it. The critical path here is not probably in lithium, but maybe cobalt and some of the other areas, other metal resources. So yeah, I think that's probably one item to recognize. When you talk about recyclability, right?
Yes.
There's one way to think about it, which is, how do we sort of, get it back to its constituents and sort of enable full circularity. But another way to also imagine this is, how do you extend the linearity, right? And what I think in areas like lithium-ion batteries is, do you have secondary utilization and other applications that can sort of extend the linear application of this value chain, right? For example, from an EV, I mean, do you have opportunities for grid scale storage, right? I mean, and does that sort of extend the lifetime of this before you have to think about recycling or enabling circular economy? So maybe that's one consideration within this, right? But yeah, I agree with you that the topic of resource constraints, especially with minerals, is something that needs to be thought of at a broader scale in this area.
I think Vijay is also somebody who's been looking at this, so maybe Vijay has a comment.
Yeah, yes, certainly. What it says is that if you look at the growth of EVs and lithium-ion batteries, it's spectacular. It's like we have not seen anything like this before. But along with that, what we also see is this tremendous effort in looking at the recycling. Now, of course, there is a sustainability angle to it, but there is also economics angle to it. I mean, the lithium prices have gone through the roof. So a lot of entrepreneurs have looked at this as an opportunity, not only from a sustainability, but also from the economic standpoint. And we see a lot of activity in this space from startup companies and big companies as well. Along with the lithium, there are alternate energy storage technologies that are being worked on as well. But I think
sodium is one. Sodium ion.
Sodium is one. There are many other technologies as well. But I think entirely different technologies. Hydrogen. And speaking about, we talked about Reliance, right? Reliance has made a huge commitment in the area of hydrogen, and that is something a lot of governments around the world have put the energy in. And so something like that, that could be a complementary technology, although clearly at this moment, the lithium-ion battery has a significant lead when it comes to EVs.
I just would like to add that the government has also notified the what they call the extended producer responsibility. It's called EPR for those who are manufacturing these batteries. So it's not enough for them to produce, but also to take care of batteries in their lifetime and recyclability and so on. So waste management is going to be a very major opportunity in terms of swapping batteries, and it's going to spawn a huge amount of business also for people who have, and technology is going to come into play. And I'm hoping that my alma mater, IIT Bombay, is going to be at the forefront of doing something, Professor Guru, hopefully.
Sure, and I'll comment on that. But Dr. Kane has his hand raised for a while, so let me hand over the floor to him. And Dr. Kane.
Yes, I have a couple of questions. First is, I think this kind of a webinar or seminar or whatever you call it is good as a refresher for those who are practicing for many years. But is this also supposed to be of benefit to students? So in that context, my first simple question is, out of the currently it is saying 64 participants, how many are students, either undergraduate or graduate? Secondly, all this information, not only this particular webinar, but the previous ones, what, if any, can be done so that the undergraduate students and the graduate students benefit from it? Maybe Guru can make some comments. In other words, I mean, it's very easy to say then you have one more elective. That's nonsense. I mean, you cannot have n number of electives. You know, already there are complaints about far too many courses. So what are the other options? Anybody has any comments?
So let me try and address that. So one is IIT has really changed a lot. IIT Bombay in particular has changed a lot from being largely an undergraduate training institution to a research university. So there's a lot more emphasis on research and a lot more opportunity for undergraduates to get involved with this kind of research. In fact, since you mentioned it, maybe I can just see if I can project a slide on this. In fact, one of the things that we are currently looking at is around some of these theme areas. We spoke about energy transition in the past. We're talking about materials. IIT is looking at these interdisciplinary materials. These are interdisciplinary areas, and there are people from chemical engineering, material science, energy sciences that are involved. And so one of the things that we're doing, as in the next few months, is to try and put together a center of excellence in materials. In fact, one of the education and outreach are big parts of this, right? So we're focused right now on plastics and polymers, life cycle assessment, looking at biological waste, so a whole range of this. And in terms of outreach and education, there are opportunities for students to participate in these. In fact, there are master's programs, projects that are part of that. One of the things that we didn't speak about is things like end of life solutions. For example, one of the big problems in plastics is them leaching it, into the environment. So, for example, things like microplastics. And we have undergraduates who are in my lab who work on things like this. So there's a lot of activity that goes on in terms of opportunities for these. In fact, this is again something that I guess it's not particularly relevant for this particular discussion, but there are ways in which we are putting together project areas and research in this that people are involved in. But having said that, I think the education part of it, in terms of floating another elective, I would not necessarily agree that there is no meaning to that. At some point, learning rigorously, for example, what are the methodologies out there? What is the state of the art? What are the challenges? This is important to learn in a structured way for undergraduates as well as graduate students, and that's really part of the endeavor in terms of offering electives. But also incorporating modules on sustainability as part of core courses, all our core courses. And there's a big initiative at IIT Bombay led by one of my colleagues, Yogendra, which is to come up with these modules that can fit into traditional undergraduate or postgraduate courses and that expose people to concepts of sustainability through that. Right.
So thank you. Now, how many students are attending this, do you think?
This I'm not sure. I'll have to find out. I noticed that there were several students who were attending, but also this is recorded. And one of the things we notice is that people come back. So in fact, today we've had about 85 to 90 participants at the peak. That in the past we've had far more participants, like 100, 150. For the first one, we had 200 odd participants. I think there is also a little bit of fatigue for online meetings. So I think people will prefer to view some of these as recordings later as well. So before we go on, I wanted to sort of take a moment to formally acknowledge the participants. We're out of time and we can continue having our discussions. But before we get into that, I thought I'd want to sort of take a moment to formally acknowledge, and thank our participants. So each of us, so right now this is an e-memento, but each of you will receive a printed version of this hopefully in the next couple of weeks. So thank you, Rajiv ji, for very illuminating, for laying out really the, what it is that we're going to talk about. So here's a note from the director. Also, Vijay, I know you're currently in Pune, but I don't know if you'll be able to mail this to you before you leave. But again, there's a note. These are artwork that several of you are alumni, and so I'm sure you recognize this is the one of the oldest parts of the campus, which is the campus temple. It actually predates IIT. This is the famous Infinity Corridor. Srini, this is the iconic main building, and Sameer, this is I don't remember which hostel you were in, Sameer, but this is the boathouse, which is now, of course, surrounded by water hyacinth, and so it's not really used as a boathouse anymore. But this is a very beautiful place for undergraduates to go in the evenings for sure. Also want to take a minute to acknowledge all the people who helped make this event possible. The department, Madhu Vinjamore is currently the department head, and he's been very supportive of this initiative. Prathamesh is our IT, our IT in charge in the department, and he helps a lot with setting up the website, linking it to our departmental website, and so on. This meeting was largely organized by the organizers, by the student volunteers. This is from the Chemical Engineering Association in the department. Want to especially give a shout out to Tejas Lokhande, who's the current alumni secretary for the department, Parth Dani, who manages a lot of the IT stuff on behalf of the students, and Kathy Jain, who's the general secretary, the department general secretary at this time. We've also got a lot of help from the Dean, Alumni and Corporate Research, and in this case, at this time, it happens to be a chemical engineer, Ravi Gudi, and his office, and also the DRF. Ravi Shankar is also an alum, and he's currently the CEO of the DRF. He's from the batch of 90. Rukmini Chopra, Deepthi Date, Prachi, and several others. And just to to name my other co-conspirators in these meetings, there's Pankaj Doshi, was my was my classmate, and Srini and my batchmate. And this was really, I think, pushed a lot by the class of 95. Sosanti, Sanat Mohanty, Jay Asundi, Sri Singhvi, Jindal Shah. These are the guys who've really been helping shape this and also really keep this whole initiative going. Janavi is a class ahead of mine. She's also joined the organizing committee, and hopefully will take the lead in one of the future ones. And my much younger colleague in the department, Bharat Sutar, is an alumnus, but also a colleague in the department. He's a faculty in chemical engineering. So thank you very much for that. And with that, I sort of formally close this part, but we leave it open for discussions for people who'd like to stay back and chat a little bit. You're welcome to do that.
I just want to say, Guru, thank you for for giving us the time and the opportunity to be part of this. Right? Maybe if I can offer just one thought, it is that till now, right? I mean, our waste streams have been quite intermingled, but our technical approaches have been quite discrete. I think going forward, I think our waste stream should be discrete, while our technical approaches should be quite interconnected. I think that's the way we develop solutions for this going in the right manner.
Absolutely, agree with that entirely, Srini.
Dr. Kane mentioned about the contribution of IIT in circularity. So I'd like to give an example of the work that has been sponsored by GRP Limited, the company with which I'm associated with IIT Bombay. So there is a department in IIT Civil Engineering which is doing some work on the use of solid waste in different applications. The company GRP has developed certain materials which are from recycled rubber and plastics, and the project aims at finding applications for these in different sectors, including civil engineering, ports, construction, and so on, so that the functionality could be utilized. and this material could be put to better use, and at the same time with the focus on circularity and recycling. So this is, and it's a partly interdisciplinary area where at some stage we might even see the Department of Design coming in, because it has to do with making prototypes, trying them out in actual applications and so on. So I think industry and IIT can work closely and develop several projects which could lead to better utilization of resources. I'll give you another example where IT is now being used in India. There is a startup which is using artificial intelligence to segregate waste. Now, as we discussed, segregation at source is very important. The quality of the plastic or whatever product that one gets at the end of the pipe is dependent on the purity of the polymer that goes into the whole process. If you have some PVC in polyethylene or PET, for instance, PET bottles have a PVC label, and if these are not fully segregated, then one has an issue. So what this company does is they have taken almost 1 million images of various types of packaging products. For instance, a parachute oil bottle will have a certain shape and a size, and so forth. And they have saved them in the memory. And then there is a conveyor belt on which various aggregated end-of-life waste would move. The camera would take pictures. These pictures will then be connected to the images saved. Through that, the material would be identified as HDP or polypropylene or LDP or PVC, accordingly segregated automatically. And at the end, you have separation. So it's a very unique way where partly optical, partly AI, and partly other principles are used. Now, this is still work in progress. They have attained about 85-90% efficiency. Their objective, of course, is to get to 100%. But I mentioned about the role of IT in segregation, even traceability. In many cases, traceability has become very important. So when a company uses recycled material, it needs to be traced all the way back to its origin. And this could be done through the use of IT. So I think there are multiple civil engineering, mechanical engineering, chemical engineering, and IIT is an ideal place where all these disciplines coexist. And of course, economics and environment. So it probably could be the right place where considerable innovation can take place in this space.
Thank you. Sameer, Vijay, any last thoughts?
No, I think, Guru, thank you for getting all of us together. I think this is phenomenal just to be with this with Vijay, Shri, and Rajeev ji. Look, I think as we kind of Rajeev ji hit it on the nail on the head, as he kind of look and move forward, right? You know, chemical industry stands in a pretty unique position as we kind of think about the broader goals of the world on decarbonization, recyclability, circular economy. You pick what you want to, how you want to label it. Industry stands in the middle. I mean, even things like hydrogen economy, we didn't go into those kind of things, but you start looking at that. They cannot happen without the materials being there. Everybody wants to decarbonize, but don't want to acknowledge the role that the chemistry and the chemical engineering kind of plays in here. I think we as industry need to do a better job at that. And I think some of the solutions that we can provide can really help solve some of the big goals that people as part of COP26 or let's see what comes out of COP27, the big goals that people laid out, they can't happen without chemical engineering. So we stand in a pretty unique position. So I'm pretty excited.
Thank you.
Indeed, what I feel is that this is the most exciting time for chemical engineering, material science. And if you look at the challenges, sustainability challenge around the world, where there's energy transition, we're talking about high energy generation, hydrogen, energy storage, talk about plastic recycle. Chemical engineering has a role to play. And one thing that it's a biased view, but I feel that chemical engineers are one of the most versatile engineering species out there.
I second that.
Evolution of chemical engineering 20 years ago, look at what IIT Bombay was doing, what top universities doing, versus now. We pivoted hard, and we're working on nano, bio, all these exciting areas. So it's really an exciting opportunity. to be part of chemical engineering and material science.
Great. So on that note, thank you. So I completely agree. Chemical engineering is really one of the most exciting areas right now, and I think it's going to be critical, right? With everything else out there, we cannot do without materials, and we cannot do without getting these materials at low cost to the environment, right? There is always going to be some cost, but it has to be minimal. And as we grow larger, I think that there's really no other choice but to go down that route. And chemical engineering is going to be absolutely critical to some of these things. I mean, Srini, no offense intended, but I'm going to sort of rope you into the chemical engineering fraternity as a material scientist as well. So,
glad to be part of the community.
Right. So on that note, I promised it wouldn't be more than 90 minutes, but we've run a little over. But it's been a very exciting, fascinating discussion.
Yes.
Thank you all for participating. I know
Thank
it's late for several of us in India. Thank you so much for taking time out on a Saturday to participate. And we will announce the next panel discussion and hope to see some of you there as well. Thank you.
Thank you.
Thank you.
Thank you.
Bye.
Thank you.